Hello everyone. Today in this video we are going to cover for the FE civil in concrete design, and for this section we'll just focus on the beam flexure. And remember that beam flexure means basically bending moment. And this is in your page 274 to 280, which cover the whole section in your concrete design, which include beam flexure, beam shear, and short columns. Okay, so the what are the things that you need to know when we talk about beam flexure in concrete design? Is the design moment capacity of your beam, which is 5 mn, and this is your design capacity. Okay, which means that your strength that your design can provide or your material can provide. So these have phi in it, which you will be getting from based on whether it is tension control, compression control, or transition control, and they lies in a range between 0.65 to 0.9. If it is tension control, zero point 0.9. If it is compression control, 0.65. And in between, then you'll get a value. Okay, so that is one that is one thing that you need to know. And then another thing is your mn. Again, this is a formulation which is already given in your FE manual for calculating the moment capacity from your beam. It can be you'll see that it is either force or tensile force into moment or lever arm distance, or it could be a compression force into lever arm distance. So all this equation is given in your FE manual. You don't have to memorize it, but just know when how to apply it. And then another thing is your once you have your design moment capacity, which means that the strength provided by material, but also we need to know what we are designing for. So which means that we need to know our demand, and by demand means your factor moment. Okay, and this factor moment correspond to your maximum moment, and maximum moment come from your different load combinations. Okay, so uh, how do you know the maximum load? That's where your understanding of your bending moment diagram is very important. Once you understand how the bending moment diagram looks like, then you can predict, or you can tell where the maximum load will happen in a beam. Okay, so we are going to use this concept, this two concept in your calculating the beam flexure. Another things that you may expect from your beam flexure is your moment ratio, or sorry, modular ratio. And this modular ratio n is equal to E, which is your Young's modulus of steel, divided by EC, which is a Young's modulus or elastic modulus of concrete. And in your FE manual, it is given what is EC, and EC is a function of your water content. Okay, so just keep that in mind, that you can expect equation for modular ratio, and that is ES over EC. And where to find EC? You can find EC in your FE manual. It is given there, the equation, and which is related to your water content. Okay, so let's look at our question here. The first question is said that is a 10 feet long. So the span length is given to you, and it is a simply supported beam. So when you read the question, try to read all the what is the information given to you. Based on that, you will know when you will be able to think and analyze like what they are asking for. Okay, so a 10 feet from 10 feet long simply supported beam with the cross section shown is subjected to a uniformly distributed load, dead load of 90 pound per feet and sub feet included, and a concentrated surface life load at mid-span. Taking your normal compression force or concrete strength, which is 3000 psi, and yield strength of steel, which is 40,000 psi, what is the most nearly maximum allowable load life load using LRFD, which is your load resistant factor design. Okay, so once you read that, then now you can now you can look at what are we designing for and what we are to find. So the first thing is a simply supported beam. That's a very important information, because how do we know which moment to calculate unless we know what type of beam we are dealing with? So here it is a simply supported beam. So this is a simply supported beam, and it says that it's a 10 feet long, so that is your 10 feet. And then this beam is subjected to a uniformly distributed service load. So you have a uniformly distributed service load. So this is a uniformly distributed service load, and because it is a uniformly distributed, we can mark this as WD, which is your dead load, and this is 90 pound per feet. Okay, just going to write here. And then after that you have and also you have a concentrated service load. So concentrated is point load, and it is at midspan. So around here, which of your midspan is going to have PL. And then after that, that's it. We have the load, and then all we need to know is what is this PL. Okay, so how do you approach this problem? We approach this problem because we need to know the factor moment. Remember the mu factor moment? It's coming from your load combinations, which has to do with your types of load that's acted on a beam. So for this kind of problem, you will have to use this for a safe design from your concrete class. You know that for safe design, your design moment capacity, what you design for, should be greater than mu. So you have to use this um, formulation in order to find what is PL. And now we are going to look at what is phi mn. So phi mn is your design moment capacity, and in this case we need to find mn, and mn here it is as fy d minus a over 2. And what is as? This is your as, area of steel under tension, and it is 3 of number 9, and that will be 3 into 1, which is 3" square. And then you have fy given to you, as is known to us. Now d, what is d? D is effective depth. D is your effective depth from the cg of your steel bar to the compression, to the top fiber of your compression side. Remember that if you in your class you see that this is your neutral axis, everything on the top will be compression, and everything under below will be tension. And we also know that concrete cannot resist tension, or they are weak in tension, so that's why you provided steel reinforcement at the bottom. Okay, so what is your D? D is your effective depth from the CG of the bar. This is your CG of the bar to the top fiber of your concrete in compression side. So that means this is your D effective depth, and effective depth is equal to 15 inch. So you have D is equal to 15 inch. And then what is A? A is your equivalent depth of your stress. Remember that in concrete we use Whitney stress block, or uniformly distributed stress distribution for your concrete in compression. And so for that we need to have A is given to you in your equation, which is as fy divided by 0.85 fc dash into b. And what is b? B is your width of your beam, and this is b, and which is equal to 12 inch. So if you put all those values together, you should get here 3.92 inch. Okay, so we know D and we know A over 2. And now question is, how do we find phi? Remember that phi is, you have this is the only thing that in your concrete, phi for beam flexure, only for beam flexure, has a value from 0.65 to 0.9. Okay, for shear, for concrete, or for column, generally we have one value. If it is purely axial column, we have 0.65, and for shear is 0.75. But for flexure, we need to ensure, or we need to calculate um, for the phi value. How do we calculate for the phi value? The way we calculate for the phi value is to see if this strain in steel is yielded or not. And if it is yielded, then does it satisfy the condition of tension control, or is it in a transition state? So here we need to find what is epsilon T, which is uh, strain in your net tensile. Net tensile means the most bottom steel in your beam. In this case, we have only one layer of steel, so it is so the most bottom layer of the steel is itself this steel that we see here. Okay, so in this equation, delta T is given, again, this is also given in your FE manual. It is 0.03 into B1, and then D minus A divided by A. And what is D? D is the effective depth of your CG, and what is DT? DT is your CG, effective depth, but for the extreme layer or the bottom layer of your steel. But in this case, we have only one layer. Because we have only one layer, so we say that your this CG of the bottom is also DT. So in this case, we say that your D is equal to DT. So if you put that value, you'll put all this value, you will get that this is equal to 6.75 10 minus 3. And the code say that, again, it is, this information is available in FM manual. If it's greater than equal to 0.005, which I would like to convert into 5 10 power minus 3, it's easy. I can see that 0.675 is greater than 5. So because this is greater than 5, this is your tension control. And if it is tension control, the code say that we can use phi is equal to 0.9. So if you put all the equation together, we know AS, we know Fy, we know D, we know A over 2, and we know phi, then we'll find that our phi will be 1408320 pound inch. Okay, because remember that all this unit are, area is inch square, Fy is pound per square inch, D is inch, A is also inch, so we have a unit inch, um, pound inch, and we can convert this into uh, divided by 12 to get feet. We can convert this equal to 117,360 pound feet. Okay, so once we have that, we have our phi mn, which is our important value. And now the next one is to find mu. So we get phi mn. Now what is mu here? Okay, so for finding the mu, we have two types of load combination. So in this case, we can separate out using method of superposition into a UDL plus point load. And if you remember in your static structure analysis, that your bending moment for UDL is this, and for bending moment of your point load is maximum at where the point is acted. Okay, so remember that for your UDL, the maximum moment is at the center, and that is WL squared divided by 8. That is your maximum moment for your uniformly distributed load. And for the point load is always where the point is acted. So in this case, the point is acted exactly at the midspan. So it will be PL over 4. So which means that your MU will be equal to WU L square divided by 8 plus PU L divided by 4. And what is WU? WU is equal to, there's only dead load, and so we use a load combination from your LRFD. There's only one equation for if there's only dead load, and we have 1.4 WD, and that will give you, and WD is 90, so that will give you 4 into 90 will be equal to 126 pound per feet. And then we have uh, PU, and PU is 1.2D plus 1.6 L, but since we do not have PD, which is concentrated dead load, so that will be 0. So finally we found that this is 1.6 P. So by using this equation, which we found here, which is 117360 pound feet, should be greater than mu, which is 126 pound feet. I'm not going to write a unit. We're going to write 126 into 10 square divided by 8 plus 1.6 PL into 10 divided by 4. And you'll see that PL must be less than equal to almost 29,000 pounds. 7360 minus 126 into 10 square divided by 8, multiplied 4 divided by 1.4 divided by 10, you should get close to 29,000. So in this case, your option will be 29,000 pound. So your maximum life load that you will be allowed for your design will be 29,000 pound. Okay, so these are types of the question that you may expect from your concrete beam flexure. So you can see that all you need to know, the things that you need to know is phi mn, how to calculate phi mn, and how to calculate mu. And phi mn, remember that phi, you need to know whether it is tension control, transition, or compression control. And how do you know whether it's which control it is? You have to calculate phi epsilon t. And if it's epsilon t is greater than 5, 10 to the power minus 3, or 0.0005, then it will be tension control. And you'll see that if it is less than 0.002, then it'll be compression control, and anything in between it'll be transition control. And then mn is using this equation, and you'll see that all you need to know is, do you know area of steel, do you know D, do you know A? And A is your equivalent depth, and also is given here for your equation. And also you'll see that in your FE manual you also have a formulation based on compression force, and both of them should give you the same result or same answer. Okay, so that is beam flexure, how to calculate the beam flexure for concrete. And then this will be another example. In this case, using again the same concept that we have applied in the previous lecture, or I mean the previous example, we can also apply here using those same concept. Okay, so here it says that find the value of phi, which is your stress reduction factor that should be used in computing the design moment for the beam section. All you need to know is find phi, what phi it is. So remember that 0.65 is your compression control, zero point 0.9 is your tension control, and these two are your transition. Like I said, how do we know how to find phi? Is we need to know what is phi t, and phi t is given to you in the equation. The equation in your FE manual is B1 dt minus a divided by a. Oh, I forgot to tell you what is b1, beta 1. Beta 1 relies on your fc dash. It is given in your table in your FE manual. If you look at the table, you'll see that it asks for your compressive strength of concrete, and for 3000 it is 0.85. So again, we'll see here what is beta 1. Beta 1 for we are given 4 ksi or 4000 psi, and beta 1 for 4000 psi is 0.85. And then what is dt? Dt is, again, this will be your d, which is also equal to dt in this case. Okay, so this will be 21.5 inch, and then a is equal to ASFY divided 0.85 FC dash into B, and this is your B, which is your width of your concrete, and this will be equal to 7.5 inch. And then AS is 4 of number 10. 4 of number 10, the area of number 10 is given in your FE manual, and this is 5.08 inch square. So if you put all this value, you should get 7.5 inch. And then if you look at your phi epsilon t, your epsilon t is equal to 4.31 10 to the power minus 3. So is it greater than equal to 2 10 to the power minus 3? Yes, but it is not greater than 5 10 minus 3. So which means that this is in your transition control. And if you look at your FE manual for transition control, phi is equal to 0.48 plus 83 epsilon t, and if you put all this value, you'll get 0.84. So your correct answer will be 0.84. Okay, so that's how you calculate the strength reduction for your concrete design. So all you need to know is whether the steel is yielded or not. If it's yielded, then is it transition control or not? Because the condition, because the requirement for the steel to be yield has to be equal to the yield strain of steel, which is 2 to the 10 to the power minus 3 or 0.002. Just because it's yielded doesn't guarantee that it is a tension control. So in order to guarantee that it is tension control, then it has to be added 0.003, which is equal to 0.005 or 5 to the power 10 minus 3. And if it's greater, then you get tension control. And if it's not, then you have your transition control. And transition control will be somewhere in between 0.65 and 0.9. Okay, so that's how you calculated the strength reduction factor for your for your uh, beam design. Okay, and then another thing that I want to say, because some of you might confuse between D and DT. If you have a beam, and let's say that in a beam you provided um, 2 layer of steel, then the CG of the steel will be over here, and this will be your D, and then the dt will be the CG of the most, or the extreme bottom or extreme layer of your steel, and this is your dt. Okay, so that's a difference between d and dt. In this case, the reason d and dt are the same is because we have only 1 layer of steel. Okay, so that is about beam flexure. And then let's do another example. And then in another example, you were asked to find what is the design moment capacity. In this case, design moment capacity means the strength provided by your concrete. So phi mn is phi, we need to know what is phi, and we can have to calculate what is mn. Mn we can calculate with as fy d minus a over 2, and this will be your d, and also this will be your dt because we have only one layer of steel. And then fy is given to us, which is 40 ksi, and fc also is given to us, which is 3 ksi. And then we need to d also, we know d here, and then all we need to find is a, and a is as fy divided by 0.85 fc b, and this is your b. And a here will be equal to as is 3 of 9, so that will be 3 inch square. And if you put all the value together, you should get 3.92 inch. And then after that, if you put here all together, you should get 2164.8 in 10 to the power 3 pound inch. And if you divide it by 1000, you should get this as 2164.8 kips inch. And if you divide it by 12, you'll get 180.4 kips feet. Okay, and so that's how you calculate it. And you can also, here you can put 2164.8 10 power minus 10 power 3 divided by 12,000 to get kips feet. It's you can do either way, whichever is, if you feel comfortable, you can go step by step, or you can do all at the same time, because you see that we divided by 1000, we divided 12. And please remember that if you use 3 ksi, then it will be kip, but here in our calculation we use psi, that's why it becomes pound per inch, and this is 40,000 psi. So one thing about FE is they really ask you to be proficient in how to use your unit. Okay, so when you're comfortable with using the unit, then you don't have to convert to psi. You can directly put 3, and you just need to know that in this case, if you put 3 ksi, then it'll become kip inch. And then for phi will be related to your strain in steel, so that will be 0.003 beta 1 dt minus a divided by a, and beta 1 is 0.85, and if you put them together, you'll get 10 to the power 10 minus 3, and this is greater than equal to 5 10 to the power minus 3, and so it is tension control, so this will be 0.9, and 0.9 multiply with 180, you should get 162 kips feet. So your option here will be 160 kips feet. Okay, and you'll see that one thing about FE in your FE exam is you also can get 180 kips feet. If you have selected C, your question would have been wrong, because KC is option C is mn, which is your nominal moment capacity. And by the word nominal moment capacity is the maximum moment that your material can resist. And the code, in your design code, we never use the nominal moment capacity. We never use the maximum moment or maximum capacity that the concrete can provide. We always use some factor of safety, and in this case it's a strength reduction factor, so we always multiply with phi. So we always underestimate the strength or undervalue the strength. If your maximum can take 180, we are not going to use 180 as your design moment capacity. We are actually going to reduce it by multiply with phi, and we actually say that, oh, our design is can take till 162 kips feet. Okay, so in that way you provide your room of factor of safety. And then the fourth one, this is a conceptual question, and in the conceptual question, um, this is where it tested your knowledge of bending moment diagram. If you remember that this is your fixed end beam, and if it is a fixed end beam, we know that from your bending moment, it is always negative bending moment, and then where the point load is acted will be positive, because we know that uh, when the load acted on it, it will sag. And remember that sagging is moment is positive, and hugging means moment is negative. And what do you mean by sagging? What do you mean by uh, positive moment or sagging? Would mean that tension is at the bottom, compression is at the top, and hugging means tension is at the top and compression is at the bottom. So if you remember from your structural analysis how to draw the bending moment for the fixed beam, moment will be negative, and then where the load applied, it will be positive. Okay, so uh, this will be positive. So if I draw it here, I will see that this will be negative and this will be positive. Okay, so negative, positive, negative. This is your bending moment diagram. So you can either start with bending moment diagram, or you can think also from how it will deflect. If I deflect, it will be I'm just exaggerating, okay, for the deflection. So you'll see that if your beam if your fixed beam is applied with a unit with a point load, it will deflect in this manner, and you'll see that these are the point of inflection where moment is equal to zero. And if I compare now, where if I once I draw the deflection, I can compare with my bending moment. Does it agree or not? If it doesn't agree, then something is wrong in your concept. Okay, so also you have done something wrong in your either in your deflection or your bending moment diagram, BMD. Okay, so in this case, let's see. I said that if it is moment is positive, it should sag. So positive moment is from here to here. You see that this is sagging, and which means that this is tension is at the bottom, compression is at the top. And if I look for this part, this looks like a half side of hugging, because if I draw the full side of hugging, it'll be this. So this is we call it, sometimes we remember that smiley face is sag, positive, or when you have positive moment in your life, you smile, so that is sagging, smiley face. And you have negative moment with frown, so that is your becoming sad, so that is hugging. Okay, so this is representation of your hugging. So and then under this hugging, you see that the bending moment is negative, and this also is hugging, so negative. Okay, so that is, so which means that our deflection moment, our deflection curve, and the bending moment, they agree each other. And now now is asking which or what is the correct location of the steel rebar against a flexural failure at AA. So you'll see that at AA, this is your negative moment. And negative moment means tension is at the top, tension is at the top, and compression is at the bottom. And so we know that concrete is very weak in tension, and because it is weak in tension, that's why we have to reinforce using steel, because steel is very good at resisting the tensile force. So in this case, you have uh, a multiple option. So let's look at option A. Option A, you're providing the steel at the top, and this is what we actually needed, because concrete is weak in tension. So so to resist that tensile stress developed at the concrete, we need to provide steel reinforcement. And so this is tension at the top and compression at the bottom, and concrete is very good or very strong in resisting the compression, so we don't have to provide steel reinforcement, um, unless you are designing for doubly reinforced. But here we are talking about singly reinforced. So that means this actually agree with our concept of reinforced steel design in concrete. So that means our option is A. Okay, let's look at option B, because sometimes just uh, just knowing the answer is good, but also we have to reason like why the option A is good or the right answer. Let's look at option B. Option B, you're providing reinforced at the compression side. So that means this steel, only one steel will resist that tensile stress, and so the crack, if you apply for this beam, you will expect the crack will develop from the side where there's no reinforcement. So that means this is not a safe design. And then what about option C? Option C, tensile concrete is weak in tension, so you'll observe crack at the top, and so this is also not a safe design. And then option D is put in the middle. It's like, well, this is safe. You can say that up in the middle it give you safe, what call it, it's most safe design, but actually no, it's not very safe design for option C, because option D, because again, concrete will generate it from the top because it's weak tension, and then it will propagate it. So in this case, it's considered as a unsafe design because you let the crack to develop and propagate it. But if you have designing as option A, then actually you strengthen that area against tensile stress, so the concrete will have more strength to resist. Okay, so that's all about your beam flexure. Thank you.